The next result is lemma 752. Now before we start proving this one, let us recall that in the previous analysis video, we proved the root test for absolute convergence of a real series. And you can of course understand that the root test is a bit difficult to apply. If you are given a concrete series of real numbers and you are asked to check its convergence, then it's a bit difficult computationally to apply the root test due to the presence of nth roots where n keeps changing. But fortunately, roots can be replaced with some ratios, thus simplifying things, and that's where this next lemma comes. So let's see what the statement is. The statement is just simply this. There are not many hypotheses or anything, only a simple hypothesis. We are considering here a sequence of positive real numbers, positive numbers that is, and this positivity is the only hypothesis. Then these inequalities are true. Now you can see that in these inequalities we see lower limits and upper limits of two sequences. Let's see what those two sequences are. We can clearly see that one of those two sequences is this, and the other one is this. So that means these inequalities are saying that the lower limit, that is the limit inferior of this sequence, is less than or equal to the lower limit of this sequence, which in turn is less than or equal to its upper limit, which in turn is less than or equal to the upper limit of this one. Again we come back to this. In other words, the lower limit and the upper limit of this sequence traps the lower limit and the upper limit of this sequence in between them in this sense. Okay, now we come next to the positivity, this condition. Positivity is assumed only so that we do not have zero denominators. If you just simply take a sequence of real numbers, maybe some of its terms are zero and they will appear in the denominator of some of these terms. So this sequence cannot be formed, it will be ill-defined. So to avoid that, we are having a positive, a sequence of positive real numbers, and that positivity also shows itself here, because you can recall that in the root test we considered this quantity, right? Based on whether this quantity is less than 1 or greater than 1, we concluded some things. In order to have a non-zero base in this power where you are calculating nth root, we had to consider absolute value. Here however that is not needed because all the cn's are positive. And finally, before we actually start proving this thing, I have changed the statement slightly, a little bit. In the text, this given sequence is this, where the starting index is some arbitrary integer m. Now you can use m. You won't have any problem forming this sequence, but here you will have a problem, especially when m is a negative integer. Say you have this -2 to infinity. Now the cn's are positive, fine, that is not changing, but when you consider this sequence, if you have this, then you would start things off with this, which actually there is no problem with this, because c minus 2 is a positive real number whose power where the exponent is 1 over minus 2 actually has a meaning. It is well defined. But then you consider the next term, and then in the next term you would have to consider this, which is meaningless. It is not well defined. It does not have any meaning. So to avoid unnecessary complexity, we have decided to take 1 here instead of a general m. And by now you already know, you have seen many things like this, that in analysis the objects that we are dealing with, whatever is happening in the beginning actually does not matter. What happens in the limit is what we are after, and that's what matters. So if you are removing a finite chunk of your object from the beginning, then nothing essentially changes. What is happening with the rest of the object, the tail end, which is in fact the part that is holding the infinity, I mean most of the object is there in this part, not on this part. That's what matters. So it actually does not matter where we start our sequence. So let us now start the proof. Now what is it that we have to do in this proof? Before we start writing the arguments, we note that we are seeing 3 inequalities which we have to prove. However, the middle inequality is something we already know, okay, from our theory of limit superior and limit inferior, namely that for any sequence of real numbers, its limit inferior is less than or equal to its limit superior. We have already seen this before. So that means there is actually nothing to prove in the middle inequality. It's already available to us. And so that leaves us with these 2. The first one we will leave to the exercises, or rather the author has left to the exercises. So we will also do that. So we will only prove the last one. So let's just start off by writing these things. Note that the middle inequality follows from that proposition number I am never able to remember. Six, 4, 12 part C, which just states this itself, that lower limit is always less than or equal to the upper limit. We leave the first inequality, that means the first one, to the first exercise of this section. And only prove the last one. So that means we are now trying to show that the upper limit of these ratios is greater than or equal to the upper limit of these roots. Okay. Now we start things off by giving a name to this. Let L denote the limit superior of these ratios. That means L is the upper limit of that sequence. If L is equal to plus infinity, keep in mind that because we are talking about the upper limit of a sequence of real numbers, all the possibilities are there. In general, this L is an extended real number. So it's not necessary that it has to be a real number. It may take those two infinite values also, any one of them. Now, if it happens that L is plus infinity, then there is nothing to prove. That's because this just like this one, L, this one is also an extended real number, and we know that in the system of extended real numbers, in that ordered set, this is the maximum, absolute maximum element. So it's greater than or equal to everything, greater than or equal to itself also. So in that case, there is nothing to prove. So we assume L to not be equal to plus infinity. Now, since L is not equal to minus infinity, so this means that L has to be a real number. Since L is not equal to minus infinity, we must have this. And now L is a real number, but there is a question. Where is this coming from? Why is L not equal to minus infinity? And the author also raises this question, and he just writes why within brackets. And to see why, let's go to the definition of limit superior. So what is the limit superior of this sequence? So you already know what the sequence is. So let me just write its terms. The first few terms, am I writing it right? 1, 2, 2, 3, yeah, 3, 4, 4, 5, and so on. So to calculate the limit superior, I mean, if we go by the very definition of limit superior, what you first do, you first let me just denote it by L1. L1 is the supremum of this entire sequence, which is some extended real number. Then what you do, you calculate the supremum of this sequence. Which is obtained by removing the first term from this sequence, and then you calculate the supremum of the next sequence, which you would get by removing the first term from this sequence. That means this, and so on. So you keep on doing this, you get a sequence of suprema, and what you do, you calculate the infimum of that sequence of suprema. That by definition is your limit superior L. Now positivity plays a very big role here. because all the terms in your original sequence Cn are positive, so these are also positive real numbers. That means this L1, whatever it is the supremum of this sequence. No, so it will be greater than or equal to all the terms of this sequence, and all the terms are all of them greater than 0. So that means L1 is greater than 0. Similarly, L2 is greater than 0, L3 is greater than 0, and so on. So when you are calculating the infimum of this sequence Ln, then you are considering a sequence of positive extended real numbers, and infimum by definition is the greatest lower bound. For this sequence Ln, you already see a lower bound 0, which is one lower bound. So the greatest lower bound L should be, because it's the greatest, greater than or equal to this lower bound 0. So L is greater than or equal to 0. So how can it be minus infinity? It cannot be minus infinity. It is a real number, and that too it's actually non-negative. So that is why L in fact has to be a real number. But here, however, we see much more, that L not only is a real number but a non-negative real number. Okay, so let me just keep it like this. It's not a part of the proof, but it's an explanation of why we have this inequality. Next. Now that we have L to be a real number, we can do our usual calculations with L. So it's time for us to choose one epsilon. That's what we always do in analysis, right? In the beginning itself, I mean, it's like we have sort of epsilon fetish. We are every time we are trying to take some epsilon, no matter what the situation is. And you know the reason also, because we are dealing with infinite objects and things happening in the limit, which we cannot express precisely using equalities or equations. That's why we take epsilon and deal with inequalities. That is, every time whatever we are doing an estimate. We are not saying that this is exactly equal to that. Of course, in the limit everything is exact. However, when we are actually calculating, when we are trying to go to that limit, we are always dealing with inequalities. We are making some sort of approximation, and we are making the error smaller and smaller and smaller, and seeing what happens in the limit. And that's why, in fact, epsilon is used. Epsilon stands for error, and along with epsilon you also know what is going to come next, or what already has come, delta. Epsilon stands for error and delta stands for difference. Okay, so now choose positive real number epsilon by proposition 6 for that thing which we have already used many times by now. There exists a positive integer n such that Cn plus 1 divided by Cn is strictly less than L plus epsilon for all integers n greater than or equal to n. What have we written here? For that, to understand that, let us quickly recall this part A, or rather that part of part A which we have used here. So what this part A says, among other things, is that if we have a sequence of real numbers, okay, and say you have L plus its upper limit of this sequence, then if you have an extended real number x strictly greater than L plus, then there exists a positive integer n such that the terms of your sequence an will be less than that x for all indices n greater than or equal to n. So in place of an, now you have these things Cn plus 1 by Cn, so that means we are considering that sequence, and its limit superior is of course L, and in place of this x you have L plus epsilon, which is greater than L. And note one more thing, that L plus epsilon actually makes sense because now L is a real number. Had this L been plus infinity, this would have been meaningless because we have not really defined any algebra for infinite quantities here in this text. So I mean, whatever we have seen so far, that type of thing has not been defined. Okay, so that's how we are getting this positive integer n for which these things are happening. That means an, Cn plus 1 by Cn, is less than x, L plus epsilon, starting from that stage and going and moving on. And there is one more thing also that we should note here. Remember, I said that I changed the index of our sequence to start from 1 instead of a general integer. So that is why this n that you see here has to be greater than or equal to 1 instead of that m. So n being greater than or equal to 1 is equivalent to n being a positive integer. That's why I am writing positive integer n. Okay, so that is our application of part A of proposition 6 for 12. We are now going to use this condition. Thus, Cn plus 1 is less than Cn times L plus epsilon for all n greater than or equal to n. Note one thing very carefully, that Cn being positive allowed us to do this. That is because to get this inequality from this, we have to multiply on both sides by Cn, and the inequality has not got reversed because Cn is positive. So for any n greater than or equal to n, we have, okay, now we are going to write something that looks like this. Cn is strictly less than C capital N times a power of L plus epsilon, which is not necessarily the first power, but rather it's this for all n greater than or equal to capital N. But then again the question is how? Within brackets I just write by induction, and that's because the author also has written it. But how exactly how? Let's just write the first few of these inequalities, because actually you can see that since this n is changing, we in fact see infinitely many inequalities here, not just one. So what is the first inequality? That is the one that you obtain by putting small n equal to capital N. This. Then the next one is this. And let's write one more. N plus 3 is less than n plus 2 times L plus epsilon. Now you can see that since we are dealing with positive things, whatever we have written here in all these inequalities, they are all positive real numbers. Cn plus 1, Cn, all these terms are already positive because they are coming from a positive sequence. Why is L plus epsilon positive? Recall that we already argued and we saw that L is greater than or equal to 0. So that's why L plus epsilon is strictly greater than 0, because that is strictly greater than L, right? So now if you see these inequalities, you can sort of use them together. First you use these two things together to write what? Cn plus 2 is less than Cn plus 1 times L plus epsilon, but that Cn plus 1 itself is less than Cn times L plus epsilon. So using these two things, you get this. Okay, Cn plus 2 is strictly less than Cn times L plus epsilon square. If we instead started with this, then now you have a new inequality for Cn plus 2 in terms of Cn. This is less than or equal to Cn times this. So that means this will be less than or equal to Cn times L plus epsilon. Already we had one L plus epsilon here, and now two more are coming. So that means 3. So in the general case, what you will get? You can guess that in the general case you will get this. Cn plus k is less than Cn times L plus epsilon to the power k for all positive integers k. And you can modify this slightly. I mean, in place of this same inequality, if you are writing n equal to n plus k, okay, if you are writing n equal to n plus k, then you have Cn here, that will be less than C capital N times L plus epsilon to the power k. Now in place of k you can write n minus n. Okay, Cn is less than Cn capital N times L plus epsilon to the power n minus n. Okay, I think I have to include the equality case here. Why I'm going to explain. We don't see the equality case here because the smallest value of k is 1. That means even in that case the n that we are taking is capital N plus 1, which is strictly greater than capital N. However, we can include the equality case by allowing for equality, because if your n is not just strictly greater than n but greater than or equal to n, then what happens if you put n equal to capital N? This becomes 1, this power, and you have Cn on this side, Cn also on this side. So actually they are equal. To allow for that, we are going to consider this. And by induction means we have to prove this. Okay, although the proof will be extremely straightforward, you can just simply see how the proof will be. You just have to write the proof for your own sake, and that's just it. So now you see how we are getting this inequality, and now we are going to further change this. Change this means we are going to change its appearance, not the inequality itself. Thus, Cn is less than or equal to A times L plus epsilon whole to the power n for all n greater than or equal to n, where A is defined to be equal to Cn time, I mean whatever you don't see here, from here, that is A. Minus n. And we should perhaps write here itself, note that L plus epsilon is greater than L, which is greater than or equal to 0. So the thing that you see here is a positive real number. So its power, whatever this n is, it does not matter. Also, presence of this negative sign also does not matter. Okay. This implies, however, it is in fact necessary to mention this fact that L plus epsilon is positive, Cn also is positive, so this power is also a positive real number, and as such A itself is positive in order to write the next thing. Because what we are next going to do is that we are going to take the nth root on both sides. This implies the nth root of Cn is less than or equal to the nth root of A times the nth root of this, which of course is going to be equal to L plus epsilon, because it is positive. For all, that also we should not forget. N greater than or equal to n. Hence, by the comparison principle, in the chapter on limits of sequences, we have already seen the comparison principle. That is, if two sequences are there whose terms compare term wise, then their upper limits and lower limits also accordingly satisfy similar inequalities. Hence, by the comparison principle, this is the advantage of having names. If results have names, it's much easier to remember and also to refer to. The comparison principle, we have what? Limit superior of the nth term of Cn is less than or equal to the limit superior of these. However, I think I need ink. Just give me a moment. However, by the limit laws, and also there is something for which I have to use the number because it has no name. Lemma 653. By these two things, actually this sequence has a limit, it's a convergent sequence. The fact that you can bring L plus epsilon outside is where we are using the limit laws, one of them. And the fact that this limit is actually equal to 1 is what lemma 653 is all about. So that means this is equal to L plus epsilon. Now we already know from our theory of upper limits and lower limits of sequences that when we have a convergent sequence of real numbers, then its upper limit, lower limit and limit are the same thing, they coincide. So that means this thing is actually equal to this thing. Hence, we will, however, write things systematically. We won't skip steps. This is less than or equal to this, however, is equal to its limit because it's a convergent sequence. And that thing is equal to L plus epsilon. So what have we ended up proving? Thus, this is less than or equal to L plus epsilon. Now finally, since epsilon is arbitrary, we have this inequality. Which is what we wanted to prove. Now this part, the transition from L plus epsilon to L, is, I hope, something you already know. If not, let me just remind you of something that we got way back when we were developing the system of rational numbers. There we proved something like this. Say you have two real numbers. For that part we had rational numbers. However, for real numbers also something similar is true, which was never proved because it's almost identical. So that's why we are not able to refer to any result here in this step, because that result is not there. Say you have two real numbers a and b such that this for every positive real number epsilon, then this implies a is less than or equal to b. Why? Because if it is not true, then you encounter a contradiction. That contradiction is rather easy to produce. Still, let me just show you. So the proof, the part that we are saying we will do for now is over here, but we are not trying to justify the last step. Say this is not true, then let me show it here itself. Then b is strictly less than a. That means because you can choose any epsilon and put here, this inequality will be true, and that is our hypothesis. Because of that, in particular, you can choose epsilon to be equal to a minus b divided by 2 also. Will 2 work? Let's just see. And that is because a minus b is positive. Now, do you have this for this particular epsilon? What will you get? Say, do you have this means say you have this, because that's what our hypothesis is. So that means a is less than or equal to, if you take 2 LCM, then you will get 2b minus b. So that means you will get a plus b here. So multiplying on both sides by 2, we are getting 2a less than or equal to a plus b, which implies a is less than or equal to minus b, which however is exactly opposite to what you have here. If this is our case, then these inequalities are not true, and that is a contradiction, and that contradiction has arisen because of our erroneous supposition, and that's why it is not true, and hence we should have this, and that's how we are getting this inequality. Okay. Now shall we go to the next? Let's just write the statement. It will be nice if I complete the section. The statement is not very big. Okay, let me just get this over with. And this next corollary to this lemma is actually what is called the ratio test, where we have another such thing like root test. This is corollary 7, 5, 3, and it's called ratio test. Let summation an okay, again Professor Tav is starting things with M. We will see be a series of non-zero real numbers. The non-zero hypothesis is required so that the ratios, absolute value of okay, let me write it completely. Whatever he has written, let me also just write. Hypothesis is required so that these ratios appearing below are well defined. Just like the root test, here also we have 3 parts which are given by bullets instead of, if you want you can write A, B, C also. Let's just write A, B. This looks weird. A. If limit superior of these quantities is strictly less than 1, then our series is absolutely convergent. Convergent and hence also conditionally convergent. That means just simply convergent. If on the other hand limit inferior of these quantities are greater than 1, then our series is conditionally divergent. That means just simply divergent. Hence cannot be absolutely convergent. I have to wrap this up. But you are, you have seen what we have written so far, so it does not matter. and part C is in the other cases we cannot say anything, that is we cannot assert any conclusion. Okay, so the series that we are given is a series of non-zero real numbers, and that non-zeroness of course is there to make these ratios well defined, and these are the conditions. Now this needs to be proved no matter how trivial it is. It in fact directly follows from the previous lemma, the lemma that we have proved today. However, it needs to be proved, but since we have been at it for some time now, in this video I am talking about this video length, so let me just stop it here. So it will give you an opportunity to think of it on your own and see how this thing directly follows from the previous lemma. After this, there is another small consequence of that original lemma, which is just this limit. One can prove that this limit is equal to 1. And after that there is a remark and this section ends, after which of course we have exercises where we are actually going to use these tests to see whether a given series is absolutely convergent or not. And one more thing, you remember that while proving the root test also, and you can see here also, there is a third case where we cannot say anything. So we have to justify that, those remarks or those sentences, that okay, why is it that we cannot say anything when in these other cases we cannot assert any conclusion. There also that alpha, when alpha becomes 1, then we cannot say anything. So we will have to provide two types of examples where alpha becomes equal to 1, but one series is convergent whereas the other one is divergent. So we will see these things, but in the next video or the one after that. So today I end things here itself, and this coming Tuesday, because tomorrow we don't have any video, this Tuesday actually, according to the sequence in which we go in these videos, Tuesday we should do vector spaces, but because one of you has already requested for calculus, so this Tuesday we are going to do calculus, and then next Friday we will do vector spaces, and then of course things will cycle back and it will go on like this. So having said that, if you want to say something about these things, you can write in the comment section below, or you can mail me at my address. The link will be there in the description. So see you on Tuesday with calculus, where we are solving some problems. Some of you are liking it, I think, so which is a nice thing. So having said that, this is just it. So until the next video, this is me, Lucifer, from a mathematical room. Have a nice night.